So, we introduced some basic tools of calculus. So, let us introduce some notations. So, by C of R, I mean the set of all functions f such that f is continuous on the entire real line R. And by C1 of R, we denote set of functions such that f prime is continuous everywhere. So, we immediately note that C1 of R is a subset of C of R. So, the set inclusion is a proper inclusion, since there are continuous functions for which the derivatives do not exist. So, we follow this notation, write C2 of R and denote the set of functions such that f double prime is continuous everywhere. We continue to use this notation and denote by Cn of R the set of functions such that the nth derivative is continuous everywhere, and so on. And by C infinity of R, we denote the set of functions for which each of these derivatives exist and is continuous everywhere. So, we again note that C infinity of R is a subset of Cn of R and so on, is a subset of C2 of R, is a subset of C1 of R, is a subset of C of R. By Cn of AB, closed interval AB, we mean all those functions f such that the nth derivative exists and is continuous in the closed interval AB. So, we shall use these notations in the course of our discussion. So, we said that we will look at approximations of functions to begin with, but we already have some knowledge about how a function which satisfies certain properties can be approximated by a polynomial, namely Taylor's theorem, which you have studied earlier, tells us how to represent a function in an interval and how much of error is incurred in approximating this function by a polynomial. So, let us look at the statement of this theorem. It says that if f is in Cn of AB, we know what we mean by Cn of AB, f is such that all its derivatives up to nth order derivative exists and are all continuous in AB, and if the n plus 1th derivative exists in the open interval AB, then the theorem says that then for points C and X in the closed interval AB, there is a psi between C and X such that the function f of x, which is defined in the interval AB, can be represented by sigma k equal to 0 to n 1 by k factorial into kth derivative evaluated at C into x minus c power k plus En of x, where En of x is given by 1 by n plus 1 factorial into n plus 1th derivative at psi into x minus c power n plus 1. So, it is for all values of x which lie between a and b such that psi lies between c and x. This term En of x is referred to as the error term, and this statement gives you Taylor's theorem with Lagrange form of remainder. So, it states that if f satisfies these properties, then for any 2 points C and x in this interval, you will be able to find out a psi such that it lies between C and x, and for any x in this interval AB, you can represent this function by means of the first term, and you observe that the first term is a polynomial in x minus c of degree n. So, you can represent this function by a polynomial, and the error that you incur is En of x. You have a control over this error, namely you can determine the number of terms n that you should include in the first term in order to obtain the error to be less than some prescribed value. So, correct to the desired degree of accuracy, you will be in a position to get a representation of the function f of x in the form of a polynomial. So, it is possible to obtain a bound on the error. So, essentially Taylor's theorem gives you a way of representing a function satisfying these properties in the form of a polynomial with, and it also gives you the bound on the error that has been incurred in such a representation. So, I shall consider f of x to be equal to log x in the interval 1 to 2. So, I have taken a to be 1 and b to be 2. Let me take c to be 1. So, this says then for points c and x. So, c is in AB. So, I can choose c to be a itself. So, I have chosen c to be 1 here. So, I would like to represent log x by means of a polynomial of degree n. So, we compute the various order derivatives. So, f prime x is 1 by x, f double prime x is minus 1 by x square, f triple prime x is 2 by x cubed, and so on. The kth derivative of x will be minus 1 power k minus 1 into k minus 1 factorial by x to the power of k, and this is so for k greater than or equal to 1. So, having chosen c as 1, we compute the derivatives at c namely 1. So, that will give you minus 1 power k minus 1 into k minus 1 factorial. So, c is 1 and this is for k greater than or equal to 1. So, let us compute the 0th derivative at 1, and that will be log 1. So, it is 0. So, this gives us f of x to be equal to log x, and that is sigma k is equal to 1 to n, because corresponding to 0 we have the value to be 0. So, k equal to 1 to n minus 1 power k minus 1 by, so I have to substitute here the kth derivative at c. So, kth derivative at c is minus 1 power k minus 1 into k minus 1 factorial by, I have a k factorial, and then x minus 1 to the power of k. That is the first term. Then the second term en of x, that is 1 by n plus 1 factorial into n plus 1th derivative at psi. So, n plus 1th derivative will be minus 1 to the power of n into n factorial, and then divided by, so psi power n plus 1 into x minus 1 to the power of n plus 1. That will be en of x, and this representation is valid for x in 1 to 2 and for psi lying between 1 and x. So, let us simplify this. So, log x will be equal to sigma k equal to 1 to n minus 1 power k minus 1 by k into x minus 1 power k, and then the next term is minus 1 power n by n plus 1 into x minus 1 power n plus 1 by psi power n plus 1 for x lying between 1 and 2 and for psi between 1 and x. So, we observe that the first term is a polynomial of degree n, and the second term, is it a polynomial? Is it a polynomial? No. Why? We have a factor x minus 1 power n plus 1 in the numerator, and we have psi power n plus 1 in the denominator, and psi is a function of x. So, it is not a polynomial. So, log x has been represented as a polynomial plus some term which we call as the error term, which is not a polynomial, and this tells you how much is this function log x deviated from its approximation, namely a polynomial of degree n. So, the error en of x is this function log x minus its polynomial approximation. So, it tells you how much this function log x is deviated from its polynomial approximation. So, we have illustrated Taylor's theorem with Lagrange form of remainder. So, let us write out this polynomial explicitly. So, when k is 1, so this gives you x minus 1, then 1 by 2 x minus 1 the whole square plus 1 by 3 x minus 1 the whole cubed, and so on. The last term is minus 1 to the power of n minus 1 by n into x minus 1 to the power of n plus the error, which is En of x. So, our goal now is to use this polynomial and the error term to compute what log 2 is. We obtained an expansion of log x in this form along with the Lagrange form of remainder given by En of x. Our goal is to determine log 2 and see how much error has been incurred in approximating log x by a polynomial of degree n. Or we would like to determine how many terms that we will have to include in its expansion, so that the error is less than some prescribed quantity. So, let us do all this now. So, let us first write down what En of x is. So, En of x is minus 1 power n by n plus 1 into x minus 1 power n plus 1 by psi power n plus 1. So, this is for x in 1 to 2 and psi less than x and greater than 1. So, let us find the bound on this error. So, it is 1 by n plus 1 x minus 1 power n plus 1 by psi power n plus 1, and it is less than 1 by n plus 1 into x minus 1 power n plus 1. Why? Psi is greater than 1. So, 1 by psi power n plus 1 is less than 1. So, mod En of x is bounded by 1 by n plus 1 into x minus 1 power n plus 1. So, now I would like to compute log 2 with the help of the expansion that we have derived, namely I call this as star. So, use star to get log 2. So, log 2 will be equal to 1 minus half plus 1 by 3 minus 1 by 4 and so on, minus 1 power n minus 1 by n, then plus En of 2. So, error evaluated at 2. We already have the expression for the bound on En of x for any x in the interval 1 to 2. Now, my question is, determine log 2 correct to accuracy of one part it 10 to the power of 8. Namely, you want En of 2 to be such that it is less than 1 in 10 power 8. So, 1 by 10 to the power of 8, which means you want 1 by n plus 1 to be less than 1 by 10 power 8. So, which tells you that n plus 1 is greater than 10 to the power of 8. So, Taylor's theorem has provided us with a nice way of representing a function satisfying certain properties by means of a polynomial, and it also helps us to determine the number of terms that we may have to include, namely the degree of the polynomial that we need to use in order to represent this function, so that the error that we incur can be made as small as we please. Let us now take another example, namely I consider f of x is equal to e to the power of x, which which can be expanded as k equal to 0 to n x power k by k factorial plus the error term, where this error En of x is x power n plus 1 into e power psi by n plus 1 factorial. So, I have used the expansion for e to the power of x and written down a representation of e power x as a polynomial of degree n, and then the corresponding remainder. Suppose we want this approximation to be accurate, to within 10 to the power of minus 6. In absolute error, we require that this should happen for every x, say in the interval minus 1 to 1. Then this tells you that modulus of En of x, which is mod x power n plus 1 into e power psi by n plus 1 factorial, which is mod x power n plus 1 into e power psi by n plus 1 factorial, since e power z is greater than 0 for every z. So, this will be less than or equal to e power psi by n plus 1 factorial, since mod x is less than 1 for every x in minus 1 to 1. So, this will be less than e by n plus 1 factorial, since e power psi is less than or equal to e for every x in minus 1 to 1. We want to find the number of terms to be included such that the error e by n plus 1 factorial must be less than 10 to the power of minus 6. This tells you that En of x would be less than or equal to 1 by n plus 1 factorial into e, and that will be less than 10 to the power of minus 6. And when you do these computations, you will be able to determine that n is equal to 9. So, we have shown using Taylor's theorem with Lagrange form of remainder that if P9 of x, that is a polynomial of degree 9, a polynomial of degree 9, because n turns out to be 9. So, if P9 of 6, which is a polynomial of degree 9, is the Taylor polynomial, of degree 9 for the function e power x in the interval minus 1 to 1, then for every x in this interval minus 1 to 1, the error in approximation P9 of x to e to the power of x is less than 10 to the power of minus 6. That is, the difference e power x minus P9 of x is less than or equal to 10 power minus 6 for every x in this interval minus 1 to 1. So, now we move on to the mean value theorem. This is how you have learnt earlier. What does the mean value theorem state? It states if f is a continuous function in the closed interval a b, and if f dashed exists in the open interval AB, then for C and X, for any 2 points in the closed interval AB, there exists a psi between C and X such that f of x is f of C plus x minus C into f dash of psi. So, in particular, if I choose x to be B and C to be A, then this tells me f of B is f of A plus x minus A into f dash of psi. Rolle's theorem, which is another important result. It states that if f is continuous on the closed interval AB and if f dashed exists in the open interval AB and f of A equal to f of B equal to 0, then f dash of psi is 0 for psi belonging to the open interval AB. The result says that if you have at A f of A is 0 and at B f of B is 0, then there is a point psi between A and B at which f dash of psi is 0, namely you have a tangent which is parallel to the x axis. The tangent at this point psi has its slope to be 0. That is what the Rolle's theorem is, and the result is immediate from the mean value theorem. If f of A is 0, f of B is 0, then there is a psi between A and B at which f dash of psi is 0.